All right, everyone, welcome back for the last talk of the conference. I'm glad that you've all stuck with us through all of this, and I think that we have a talk that I'm really excited about to close this out. Tikhon Jelvis will be talking to us about reasoning under uncertainty. Tikhon is a member of the Haskell Developer Committee, and he's been using Haskell professionally as well as writing about it on Quora and Stack Overflow. So, Tikhon, I'll turn it over to you.
Perfect. Thank you. Yeah. So I know that the kind of the title of the talk is a bit vague, right? But the the topic that I want to focus on is kind of introducing a pretty standard set of abstractions that people use to make decisions and to understand systems that have some amount of uncertainty. And in the past, I found that taking mathematical ideas from other fields and expressing them in Haskell is a very effective learning technique for really understanding the abstractions themselves. So I'm using this talk as a sort of way to walk through some of these ideas and turn them into something more concrete by writing Haskell types and functions to work with them. Of course, the first question that really comes up when we talk about this is just what do we even mean by uncertainty? In some sense, we all know that in the world, there are lots of things that we don't know and lots of things that we can't necessarily predict. But going from that to something more concrete that we can act upon is difficult. And in this particular case, when I'm talking about uncertainty, I'm sort of talking about two related things, right? There's going to be times when there's simply unknown information. So we don't have a full picture of what's going to happen. We only have partial information that we can use to make an inference or make a prediction. And then also I'll be talking about randomness. So sometimes it's not even that we have partial information, but it's just that whatever is happening in the world is impossible to fully predict or happens randomly. And I'll just walk through a few specific ways, a few specific frameworks we can use for behaving effectively or for building systems that behave effectively despite some amount of unknown information or some amount of randomness. So how can we account for the fact that we don't have full certainty about what's going on, but still make good decisions, or at least make decisions that are as good as they could be in the circumstances? As it happens, probably the most basic building block for any kind of formal modeling of uncertainty is probability. And here I'm going to assume that people are familiar with the basic ideas behind probabilities and probability distributions. And one thing I like to think about quite often is just visualizing what a probability distribution is. And here's kind of a simple graph that captures a good intuition where we're saying we have some set of outcomes, x, going along the x-axis. And we're saying that different outcomes have different likelihoods of happening. And in particular, if we only do something once, we'll only get one single concrete x out. But if we don't know what that specific x will be, or that x is random, we have to be able to reason about the probability of different outcomes and the different weights depending on which outcomes are more likely. So the first step to building any kind of code like in Haskell to deal with uncertainty is going to be using some kind of type to work with probability distributions. So let me walk through a couple of simple examples using this Haskell library called monad base, which gives us several different types for working with probability distributions, all of which form monads. And we'll see a little bit down the road why that's actually a very natural model for working with probability. But even ignoring the kind of somewhat Haskell-specific idea of treating distributions as monads, just having a concrete type for probability distributions, and in particular, having it polymorphic. So we can have probability distributions with any kind of outcomes, ends up making any kind of code involving probability much easier to organize and much easier to read. In practice, if you only have some kind of ad hoc way of dealing with distributions, maybe all you can ever do is sample, so you just sprinkle your code full of calls to random.sample, it can be really hard to take that code and interpret it in some other way. But by having an abstraction that can cover any kind of distributions we care about, while also being polymorphic itself and letting us interpret it in different ways, turns out to be extremely useful. But let's actually walk through a couple of examples of probability distributions that hopefully people are familiar with. So the one I have on screen right now is what happens if you roll a fair six-sided die, right? The idea is that we have 6 outcomes, 1 through 6, and each of them have an exactly equal probability. It's what we call a uniform distribution. And this by itself is pretty easy to reason about, but things get a little bit more complicated quickly as soon as we start combining multiple distributions, so multiple sources of randomness. And another example distribution that anybody who's played Monopoly should be familiar with is what happens when we add the results of 2 die rolls together. And immediately we see something interesting. We started with 2 uniform distributions, and when we added them, the average outcome of the sum is going to be the same as the sum of the averages of the 2 individual dice. However, the shape of the distribution becomes totally different. So despite the fact that we started with 2 totally flat uniform distributions, as soon as we combine them with even this relatively simple plus function, we get some kind of totally different shape. Now, the cool thing about having a library in a general purpose language that lets us describe distributions like that is that we can take more complicated logic and still describe it in a distribution shape. So I have a slightly contrived example. Let's say you have a game where you roll one six-sided die to decide how many dice to roll, and then you just sum up the result of that many dice, right? And here what we see is that, n is the first die roll. That's going to be 1 through 6 to tell us how many subsequent dice to roll. And then we're just going to replicate the die distribution that many times and return its sum. The surprising thing here is that even this relatively simple game, it's a very short program that describes it, gets a distribution that starts looking quite complicated. It loses symmetry, and the actual shape of the distribution quickly becomes quite a lot less regular than the previous ones we saw. And this really describes, or this example really captures a lot of what makes it difficult to work with probability, and that is that even relatively simple interactions can result in quite complicated distributions. Now, as I mentioned, the whole idea of having a probability monad is actually very natural, not just in Haskell, but in the whole area of probability. And the reason for this is that we have a very important distinction between 2 kinds of random variables. There's random variables that are completely independent, and these are the ones that are important but more complicated to deal with, we have variables whose actual distribution depends on the outcomes of other variables. And systems where variables depend on each other are some of the ones that are both interesting, because in most real-world systems, there's some level of dependency, but also quite difficult to reason about. But let's take a step back. If I have 2 distributions of x's and one of x and one of y, right? Well, what does it mean if we say that y depends on x? Well, first, we have some distribution of x's. That's going to be mx. Then we have a distribution of y's, but crucially, we're saying that the distribution of y's depends on x. And in functional programming, whenever we have one value that depends on another value, the most natural way to express that is with a function. So we're going to have a function which, given an x, gives you a distribution of y. And this function captures what it means for y to depend on x. But of course, what we really want to do is some way to take the full distribution of x's, take this function that captures how y depends on x, and combine it to get a distribution of y's in terms, a distribution of y's based on the full distribution of x. And so to do this, we need a function that lets us combine an mx and an x to my and get an my out. Now, what does this function look like? So if you've been using Haskell for a little bit, you should see that this function is actually exactly the same as monadic bind. So the fundamental idea in bringing probability to the Haskell world is that the fact that probability distributions form a monad actually exactly captures what it means for distributions, or I guess for random variables, to depend on each other. Now, of course, at the same time, there are going to be cases where we want to work with just purely independent random variables. And if two variables are independent, well, what can we actually do with those variables? And it turns out that we can't have the distribution of either variable depend on each other, but we can still apply functions to both of those variables. The example we saw of adding two dice together did exactly this. It took two completely independent die rolls and summed them up. And to be able to do something like that, we need a function that can take two arguments, apply them to two distributions, and give us the distribution of results. And if we look at this function, this is actually exactly the kind of capability that we get from applicatives. So as it happens, there's this really powerful relationship between the, I guess you could say, categorical structure of a distribution and how it behaves in terms of probability. In particular, if we can write a program using some set of distributions, but only ever using the applicative operations, then we know that those distributions are independent. On the other hand, if we have some kind of dependencies, then we have to take advantage of the monad instance of our distribution type. So there is a whole research area of writing code to deal with complicated random distributions. And in this talk, we're just going to sort of take for granted that we're able to express complicated distributions and do useful operations with them. But if you're interested, I highly recommend this paper called Practical Probabilistic Programming with Monads as a good introduction to how you could take the ideas in the probabilistic programming research space and bring them to Haskell as just a normal library. I think it's incredibly elegant. However, just being able to reason about a distribution of outcomes isn't really enough to help us behave effectively or to help us optimize our systems when, in the presence of uncertainty. And the piece that's kind of missing is that in most cases, we don't actually care about a single outcome. Instead, we care about a whole bunch of subsequent steps or subsequent events, each of which can have some amount of randomness. So we need some way to not only deal with uncertainty in the form of a single probability distribution, but also some way to deal with uncertainty over time. And in the real world, there are a lot of examples of systems that behave this way. So I know a lot of areas in finance, for example, when you're trying to trade stocks, you don't just care about the final distribution of the price of some security. You actually care about how those prices move over time, because how they move over time can really inform kind of how much money you make or you lose and how much risk you're exposed to. Similarly, in a lot of industrial applications, we have systems like in retail, for example, we need to manage inventory, but we don't know exactly when somebody's going to buy something. So day in, day out, we constantly have to make decisions based on some kind of partial knowledge of what might happen in the future. And in order to make decisions like this, we need some way of describing how our system actually evolves over time. Now, as it turns out, there are actually a lot of different frameworks you could build in order to understand how systems randomly evolve over time. And it really comes down to the structure of the system you're trying to analyze. Do we want to deal with time that is continuous? Or do we just want to have a system where we have a whole bunch of discrete steps, but we don't necessarily care about the duration of any given action? Similarly, do we have some kind of simple discrete state that can describe our system completely? Or do we need something more complicated? And finally, a really important consideration is that, is the state of our system sufficient to describe how it'll evolve moving forward? Or do we need to know everything about the history that brought us to the point we're at in order to make predictions about the future? And as it happens, each combination of decisions you make along these axes is going to lead you to different research areas. But I'm going to walk through a framework that is basically the simplest set of assumptions you can make along these lines, which is a very important point in the design space because it is still expressive enough to model a lot of real-world systems in industry, in finance, even in games or video games, right? But at the same time, because it's simple and restricted, it's much easier to work with and makes it easier for us to do analysis and to do optimization. Now, what I'm going to be talking about are Markov processes, right? And the idea with Markov processes is that we're going to go through the three axes that we had and choose the simplest one at each step. So time is not going to be continuous. We are going to treat time as a discrete set of states. So there's no durations, there's no continuous time. We just go from one state to another. Similarly, for states, we're just going to assume that states are discrete and that we can fully describe the state of a system. Now, in the real world, it's often the case that we only have partial observations of what the state is. And again, there is a whole research area around partially observed systems. But for the sake of this talk and the sake of the Haskell code I'm showing, I'm going to assume that we have full knowledge of the state, and also that the state at any given point is all the information you need to know how the system might evolve in the future. So let's put these ideas together and actually see how it turns into a Haskell type. The idea with a Markov process is because we have time as just a succession of states, we can express that as a step function that describes how to move from one state to another. So to do this in Haskell, we're just going to say that a Markov process for some kind of probability type M and some kind of state type S is just a function that takes the current state and gives you a distribution of the next subsequent states. So just S to MS. And from this type, we see a few important things just from the type signature. So for example, we see that the next state depends on the current state. So the evolution of the system isn't fully independent. And we can't just jump far ahead and make assumptions about how the system works. Instead, we have to understand how the states go from one to the other. However, we also know that because this function takes a single S as an input, the distribution of next states can only depend on information encoded in the current state. And if we had some kind of system that had to keep track of the full history or was sensitive to history, we would actually have to change the type of this Haskell function. And then you could tell just from the type itself that we were dealing with something more. So for example, if we really did need to know about states in the past, this function would actually have to take something like a list of states as an input. And because we're restricting ourselves to a single state, we get what's called the Markov property, which is to say that the process doesn't have any extra memory that's not captured in the state itself. And the next question is, once we have this step function, what do we want to do with it? And the basic idea is we just want to reason about what happens when you step multiple times over and over and over. So you start with some starting state, then you have a distribution of next states. Then, based on that distribution of next states, you have another distribution of states 2 time steps from now, and so on and so forth. One way to put this in sort of functional terms is that we're going to be composing a whole bunch of functions of the type S to MS. And again, this kind of composition, the shape of the composition should be familiar, because composing functions that take some input and return the output wrapped in some monad is exactly what monads are for. So as it happens, the fact that in Haskell we can express probability distributions as monads also means that we can use all of that monad machinery to easily work with Markov chains. So I know that this is pretty abstract, so I'm going to show off an example based on inventory control in retail, which is an area I worked in for a couple of years. So we're going to take a very simple kind of inventory system, and turn it into a Markov chain that we can then reason about, or we can run simulations and understand how the system behaves. Now, for the sake of keeping it reasonable, I'm just going to have a system where every single day, sort of 3 things happen. First, at the beginning of the day, we're just going to order 3 new items. I guess I should say that in this example, we're going to pretend that we're managing a single item at a single store, and we need to understand how to order those items and whether we'll actually make money based on our costs. So the first step to doing this is just building the simple model of what actually happens day to day. And what we're going to say is that at the beginning of the day, we order 3 items. It's kind of a somewhat arbitrary number. Then during the day, we're going to sell those items to people who come to the store. But the thing that makes this problem difficult is that we can't really know when somebody is going to want to buy one of these items. So the distribution of demand for any given day is random. We can make some kind of predictions. We can have a forecast and a distribution of demand, but we can't know exactly. Then, after we're done selling for the day, we're going to receive the order we placed and just repeat and do this day in, day out for some amount of time. So to start, we need some kind of demand distribution. And for the rest of the examples, I'm just going to be using this specific distribution, which is actually pretty realistic to how items behave in retail. And it's the details of the Poisson distribution aren't very important, although it is probably useful to remember that on any given day, we'd expect the average amount, that is the average of this distribution is 3. So on any given day, we expect to sell 3 items on average. So how do we take these steps I outlined and turn them into a Markov process? Well, it's actually pretty close to just transcribing my list of steps into perfectly normal Haskell. So, oh no. Oh, I'm sorry. Yep. Sorry. Yeah. So it's just equivalent to transcribing the things the steps I went through into Haskell. So let's take a look. This code in particular is going to look just like monadic code you write in, well, pretty much any kind of monad. And in fact, if you're keeping track, you'll notice that we're not using anything probability specific in this example. All we're doing is using do notation, which means M has to be a monad, but we're not even relying on the fact that that monad represents a probability distribution. So here's how the code works. We say, well, we start with some inventory at the beginning of the day. That's the input to our step function. Then we order 3 items. We calculate how much was demanded. We calculate how much we actually managed to sell, because it's possible that we don't have enough items at the store to actually satisfy everybody every single person that wanted an item. And then finally, we compute the state for the next day. And that state is going to be how much we started with, minus how much we managed to sell, plus how much we managed to order. So this is actually a pretty simple system, but as we'll see a little bit later, we actually, the behavior it has over time actually gets surprisingly complicated. But of course, to see this, we need some way to simulate the system, right? And in the case of Markov chains, as I mentioned, the way to simulate the system is just to apply the step function over and over. And so in this code, I'm using a streaming library called streaming, appropriately enough, to take care of the incremental application of a function kind of to itself. And the simplest way to do this, perhaps, would be with a recursive function where we just say that we have some state, then we're going to get the next state from the distribution of states that the step function of our Markov process gives us. So that's the step process state. Then we will just yield the next state. So then in the stream, we can actually see what the simulation is doing. And then we'll just recurse. And we'll do this over and over. And if we look at this, it's got a pattern that should be pretty familiar. So we have some start state, then we apply step to it, then we apply step to the result of applying step to the start state, and so on and so forth. And if this were a normal function, this actually would fit perfectly into a function we have in the Haskell standard library called iterate. And it looks like this. It just takes a function and applies it to its own result over and over and over and produces a list. Unfortunately, we can't use this function directly because we need to deal with the random monad. But as it happens, the streaming function provides a monadic version of our simulation function. So we can turn that is, instead of writing a dedicated simulation function, we can actually reuse this much more general function that works for any monad. And the reason we're able to do this is because probability distributions in Haskell are part of this abstraction that we use all over the place. So here's an example of a single trace of our system. So this is how our inventory goes up and down during the day. And despite the fact that the actual logic is very simple, we can see that the random behavior is kind of hard to predict and pretty noisy. And what this means is that we can't really make decisions based on a single trace. We have to see what happens when we run multiple traces. And well, I mean, this is what happens. So if we just try to run multiple traces, we see that they really start going all over the place. And the only good way to understand a system like that is by having some kind of aggregate statistics over a large number of traces. And we can see this in action, where if we take the mean inventory over 10 traces, we still have a fair amount of noise, but there's a clear pattern emerging. And if we do this for 100 traces, it gets better defined. And if we end up going all the way to 10,000 traces, we just basically get a line. And what this is telling us is that the simple code we wrote, while it looks chaotic on any given trace, on average, it pretty much behaves like a linear function. And if you remember, this function is graphing the amount of inventory we're holding. So the fact that our inventory keeps on increasing in a kind of unbounded way should be something of a red flag that the way we're managing inventory isn't very good. Now, that specific example, well, actually, another important thing is that if we were only looking at a single trace of data, we wouldn't be able to clearly see this relationship. But as soon as we run a bunch of traces, the behavior becomes really easy to spot. And while this example is kind of simplified and not super realistic, in the real world, somewhat more complicated systems are really, really difficult to understand without simulations. And so it turns out that even if all you end up doing is writing a good simulation of your system, you can still get a lot of useful results by being able to predict how it behaves. However, in this case, I want to go from just predicting how a system behaves to actually being able to change it. Now, the thing with optimization, right, is we really need multiple pieces we haven't talked about yet. And the first one is we need to figure out, what do we actually want from our system? What do we want to accomplish? So we need to take our Markov process type and extend it so that we're actually measuring something that we then want to improve. Now, traditionally, what this is called is a reward. And the idea is that instead of just going from a state to a state, each time we make a transition, we also accumulate some kind of reward. Now, if you look at this type, it looks like it'll be a little bit messy to work with because we have to manually pipe through the reward as we're going along. However, if we take a look at the shape of the type, we see that it looks really familiar. And in fact, the right-hand side of the type is exactly the same as a writer T specialized to reward. So what this means is that in order to deal with Markov reward processes, in order to accumulate rewards, we can just take the Markov process type we already have and apply a writer T reward to the probability monad type we were using, which then means we don't even need a new type at all, and we can just have purely a type synonym. And this is cool because it means that all of the code that we would have written for normal Markov processes almost definitely works in a very straightforward way, even when we start caring about accumulating rewards. And then, you also need some helper functions. And in particular, I like to have a function that wraps up accumulating the reward that we're accumulating to just limit the amount of noise in my domain-specific code. Of course, whenever you have a system, it's always important to ask yourself what the reward should be, because choosing the reward you're going to maximize can really affect the overall behavior of the system. And in this particular case, we're going to keep track of a few different quantities. We're going to keep track of how much money we make each time we sell something. We're going to keep track of how much it costs us to buy inventory, and crucially, how much it costs us just to hold on to inventory. So that helps us avoid accumulating too much inventory over time. And then finally, if we miss some demand, we're going to penalize ourselves because we are thinking that, hey, if somebody comes to our store and can't find what they want to buy, they'd be less likely to come again in the future. So we haven't just missed a sale, we've also made one of our potential customers unhappy. So here's an example of the code, which is exactly the same logic as I had previously, except I sprinkled in a few reward lines, a few reward statements to help us see whether or not our system is working well according to this metric. And here's one trace where in purple, I traced out the inventory, and in blue, I traced out the reward. And looking at this single trace, we can kind of tell that maybe it's not great, but it seems to be positive. But as with any kind of other random system, a single trace never tells us the full story. So let's go through the same practice of running a bunch of these simulations to understand whether or not our system actually behaves well. And once we run a bunch of traces, we see that eventually, according to our reward metric, we actually end up in the negative on average. So that's a bit of a problem. And with these simulations, we're realizing that, hey, the way we've been managing inventory in the past isn't really working. So what can we do about that? Of course, to do something, we need some way to make changes to the system as it's going along. We need to extend our Markov reward process framework with some kind of actions that we can take. And the simplest way to do that is to have a different kind of process where each step not only has the state, but also gives you another input, which lets you do something, some kind of action. And the outcome of the next iteration of your system, the next step, is a function of both where you start from and also what action you take. So now we have a system that doesn't just evolve by itself, but at every step has a hole that you can fill with whatever you want or whatever you can to affect how the system behaves. And of course, we can do the same kind of rewrite going from the MS reward to a writer, which just makes a lot of the logic much simpler down the road. Okay, so what do we do now? We have this framework that kind of lets us take actions, and we know what we want. We know that we want to improve our reward because we designed a reward metric to represent whatever we're trying to achieve. And we also know what we can do. What we can do is whatever set of actions our system permits at every single time step. Now, combining the two, we find that our goal now is to figure out how we can choose an action that maximizes our reward at every step. But in particular, we don't necessarily care about the reward at any given step. Instead, we want to find some way to maximize the total expected reward of our system. Or bringing it back to the inventory example, we kind of want to figure out how we would manage our inventory. How much should we order at each timestamp in order to, have a good store experience and make money? But how can we actually do this? How can we specify what we should do? At first, you might think we could do some computation and come up with a list of actions that says, hey, for the next X days, here's exactly how much you should order. But the problem with this is that the best action to take almost definitely depends on the state you're in, and the state you're in is random. So we can't just figure out exactly what we want to do ahead of time. Instead, we need some way to capture the fact that the best action depends on the state. And as I mentioned, whenever we're talking about, in functional programming, something that depends on something else, the way we do this is with a function. So we need some kind of function from S to A. And in the in the field of Markov decision processes, these kind of functions are called policies, right? And conceptually, what we're saying is because we don't know what the random state is going to be in the future, we need to figure out what we're going to do for every single possible state. And with this idea of a policy kind of capturing what it actually means for us to make good decisions, we now have the actual optimization problem that we're trying to solve. We want to find the policy that maximizes the total expected reward that we get. Now, a really important idea here is that once we have the policy, we can apply the policy to the Markov decision process and get a Markov reward process. And remember, this is the process that we already know how to simulate. And we get this Markov reward process that represents what would happen if we ran our system with the specific policy. And while this might sound complicated, the idea is that all we're really doing is at every single timestamp, instead of being able to pass in an arbitrary action, we're always going to look at the current state S and pass in the action that the policy tells us to do at S. So here is the same store example, except with all of the ordering logic kind of factored out. So instead of always ordering 3, we're going to take the amount we want to order as an input. And what this lets us do is it lets us write policies that then tell us how much to order in the future, purely based on how much inventory we currently have. So the policy we were using previously to always order 3 is can be expressed like this. We're saying if you always want to order some specific amount, well, it's actually just a constant function. You ignore your inventory and you order that much. So again, here is what happens if you try to order 3 and you ran something like 10,000 traces and found the average reward over time. It looks pretty bad. What happens if you try to order 4, for example? Well, it's actually even worse. Maybe we should order 2 instead, but turns out that 2 doesn't work that well either. And in fact, if we really look at a whole bunch of different quantities that we can order, we're finding that 3 is by far the least bad, but we definitely need some kind of a more complicated ordering policy in order to do well, right? And if you take a step back, what we're kind of doing here is a very ad hoc optimization where we're just trying a few different policies and choosing the best one. And so far, we've realized that just ordering the same amount every day does not work very well. So another really simple rule we could have is what's called an order up to rule. So instead of always ordering the same amount, we can choose a level, and as soon as our inventory falls below that level, we order back up so that we have enough inventory to be back at that level. And this is a very intuitive policy because it just means you're saying that, hey, at my store, I always want to end up with 6 items at the store, and that's the amount I want to keep. So whenever I sell anything, I'm going to replace it. So with this kind of policy, we can actually try, again, a few different values to see what happens. So here's another example where we have inventory in purple and a reward in blue. And this is what it would look like if we ran a single trace ordering up to 6. And again, we can't reason based on a single trace, but if we ran a bunch of simulations, we'd find that ordering up to 6 ends up consistently losing money, at least based on our reward metric. However, we could go ahead and try a whole bunch of different policies and see what the different effects are. And if we did this, if we tried ordering up to, we just ran simulations ordering up to anywhere from 4 to 16, we see that there's actually a pretty large spread of the rewards that we get over time with these different policies. And so just taking this kind of somewhat ad hoc grouping, we can simply choose the best one, which turns out to be ordering up to 10, and then use that to manage our inventory instead of always ordering 3. And then once we do that, we expect that the system as a whole is going to run a lot better. And again, here's a little graph just for intuition of what happens when you actually try to order up to 10. And the thing is a bit misleading because in this specific trace, it looks like our reward kind of stayed pretty flat on average. But again, because we've run a whole bunch of simulations, we know that we're actually doing well over time. And just going back, kind of what we did in this case is a bit of an ad hoc search through the space of possible policies. You can imagine that we just did a whole bunch of simulations with different ideas for how we could order and just chose the best one. And this isn't really a very generalizable kind of optimization technique, but in practice, for a lot of problems, it can work surprisingly well. If you have a good intuition for how a system should behave, and you just want to tune a few parameters, then running a bunch of simulations to see which parameter works better is actually a totally viable way of making decisions. Of course, you might want to know what is a more systematic way to find good policies or even find provably optimal policies for a given process. And especially, you might want to know, how can we do this for systems that are too complicated to have a good guess or to run too many simulations by hand? And as it turns out, there is a whole research area around this. And I'm not really exaggerating, there's really multiple research areas all focused on different ways to find optimal policies to act under uncertainty. In the real world, a lot of problems get solved either with just heuristics that are tuned to whatever real world problem you have. So for example, in retail, we could have heuristics based on our shelf capacity, how much demand do we have, and whatever else. And there are also often domain-specific algorithms in the research literature that solve specific problems. But there are also whole families of algorithms like dynamic programming and linear programming and reinforcement learning that aren't specific to a given problem, but tend to do pretty well for different kinds of problems that you throw at them. And so by being able to formulate your problem in the framework I just described, you're actually able to throw a whole remarkably wide range of different algorithms at your problem to help you figure out the best way you can act and how you can maximize whatever reward metric you're going for. Okay, and so that's actually the end of my talk. I know originally I wanted to cover a few examples of these until I realized that 45 minutes is barely enough to give you the framework as a setup. But once you have the framework and you can express your problems, then you can take a look at these algorithms to see how you can actually optimize your actions.